tell a real scientific and I think public policy success story, and it's about the ozone layer. You can see the globe here. We divide the atmosphere into a variety of layers. The troposphere is the lowest layer. It's where all of our weather occurs. The stratosphere is the next layer up, and that's what I'm going to really focus on because that's where most of our atmospheric ozone is located. Now, ozone is critical in our atmosphere because it screens ultraviolet radiation. Ultraviolet radiation, these are energetic solar photons. They are strong enough to break the bonds of biologically active molecules, like DNA, for example. So if you decrease the amount of ozone, which is screening this UV radiation, you can get more at the surface. And what that'll do is that you sunburn a little more quickly. For example, a person like me, I'm out for about 15 minutes and I'll get a sunburn, but it does a lot of other things. It impacts crops. It can cause cataracts. There's a famous study of watermen out here on the Chesapeake Bay in which they found that their amount of time on the bay was proportional to the cataracts that they got. The longer you were out there, the more cataracts you got. But that's extended exposure over years. So ozone is really a critical gas in our atmosphere. In 1974, these two gentlemen on the right, this is Sherry Rowland and this is Mario Molina, they proposed that there were a class of gases being emitted into our atmosphere that could destroy the ozone layer. These are chlorofluorocarbons, or CFCs. So they proposed this, and it was quite controversial at the time. They took a lot of heat because this chlorofluorocarbon industry, the chemical industry, it was used in a variety of different kinds of products. You can see some of these. Many of us remember it used to be used as a propellant for hairsprays and deodorants. It was used to make foam products like these cups that you would get from McDonald's or other companies. It was used, CFCs were used in air conditioners and in car air conditioners. It was also, there's another kind of a gas called a halon. Halons are used in fire extinguishers. They contain bromine. They can also destroy ozone. So this was proposed in 1974, and there was a huge amount of energy and effort that was going in the late 70s and the early 80s to see what the impact is on ozone, to measure ozone and these gases in particular. Now, in 1985, there was a publication of a paper on ozone down over Antarctica. And these three gentlemen here, this is Joe Farman, Brian Gardner, and John Shanklin. They're standing in front of an instrument that measures the total amount of ozone between the surface and space. And they published their data. And you can see it here. This is a measurement. This is the total amount of ozone between the surface and space over this station. It's Halley Station down in Antarctica. And what they showed was that the level of ozone was dropping, and it was dropping really fast. Okay? It was an amazing study that they published, and the quality of these data are such that there was no dispute to this. Ozone was going down, and it was going down fast. This was a real shock to the atmospheric community when this paper was published. Shortly thereafter, and this was in 1985 also, a scientist at the NASA Goddard Space Flight Center, P.K. Bhartia, made an image of what this ozone looked like over Antarctica. And so you can see Antarctica here in the center, South America, Africa, Australia, and here in the middle is this very low ozone area. These red colors and yellows that you see here indicates very low ozone. And it was dubbed the Antarctic ozone hole. So ozone was going down fast, and it was a huge region. This is a very large region, comparable, this continent of Antarctica is a large area, so there's a large depletion over a large area. And we didn't actually understand what was going on at the time. But within a couple of years, we figured out it was actually due to these chlorofluorocarbons and halons. So there was a lot of consternation about this. What are we going to do? How can we stop it? What other measurements can we make? So the rising concern about the problem amongst the nations of the world, there was already discussion about should we get together and create an agreement. And in fact, after a couple of years, they did create an agreement. This is an agreement called the Montreal Protocol. These are, shows a meeting of the parties to the Montreal Protocol. It took place in Doha on the Saudi Arabian Peninsula. And here you can see the Montreal Protocol had a series of agreements, the initial one, and then they were added on to further strengthening regulations of these chlorofluorocarbons. So eventually, the production of chlorofluorocarbons and halons was fully agreed to. Now you can see the nations of the world, there are little signs here. Here you can see, this is me sitting way in the back of this meeting. Even though the scientists, we bring them all the information, we're always put at the back of the meeting. You know, when they need us, they'll call on us, but we sit in the back and listen to all the discussions. And most of these discussions are about a country's ability to maybe use a CFC for a short time. There are a lot of different things going on in these meetings. Okay, so now what's happened with ozone? Well, first of all, let me talk about chlorine. So chlorine, it was going up and up and up through the 1960s, 1970s, 1980s. These are a combination of all the CFCs and halons. And then the Montreal Protocol was signed here in 1987. And slowly those regulations began to take hold. And in fact, the projection is that these ozone depleting substances are going to decline with time. Now this is going to take a long time because CFCs, these chlorofluorocarbons, have long lifetimes. For example, CFC 11 has a lifetime of about 52 years. CFC 12, which was used in your car air conditioners, has a lifetime of over 100 years. So it's going to take a long time. Even though the production and emissions of these gases has been regulated, it's going to take a long time for them to come out of our atmosphere. So what's happening with ozone now? So this is showing, this is in percentage, the change of ozone over time in percentage. And you can see the observations as you go into the 80s. You can see that ozone was going down, the CFCs were increasing. The Montreal Protocol is signed here. Pretty soon the chlorine has started to decrease. And you can almost, there's a Mount Pinatubo effect right here, but you can almost see that ozone isn't going down anymore. And maybe there's a hint that things are starting to go up. We can't say that, as scientists, we can't say that's true yet. But I think we're getting to the point, within the next few years, I think we'll actually be able to say, statistically, that ozone is increasing in our atmosphere. Let's keep our fingers crossed. Now, the other way of looking at this is we can use a model to take a look at what would have happened to ozone if we'd done nothing. So I'm going to show you a little model study here. And on the top left, I'm going to show you the expected world. And this is with the Montreal Protocol. CFCs are going to decline. Over here is what we call the world avoided, and this is chlorine going up. If you look on the picture, you can see the amount of chlorine in the expected world and the amount of chlorine in the world avoided. So you can see here it's 4.5. There it's already a little bit higher because of the Montreal Protocol. If this is because of the Montreal Protocol, that's without one. And you can see it's flying by fairly quickly. As you can see the date on the right, you can see the ozone hole appearing every year. Chlorine continues to go up in this world avoided. And now you can actually see it peaked out at about 4. And it's in a slow decline as we're out to 2022, 24. If you look here at this world avoided, you can now start seeing a little ozone hole, deep, low values appearing over the Arctic. And you see the very, very large ozone loss over the Antarctic region. If you look at the expected world, you don't see any of those things. And in fact, as chlorine continues to increase, you can see ozone going down now in the tropics and in the subtropics. So you can see that here you're dominated by reds and oranges, the higher ozone levels. In the world avoided, you can see that ozone is declining and declining and declining. Now, this is about 40 to 50 times, by the time you get out to 2065 here, this is 40 to 50 times the natural level of chlorine in our atmosphere, chlorine and bromine combined. And this has gone down, it needs to go down to about 1.2. This is about halfway there. But you can see the difference in ozone. 65%, or excuse me, about 2/3 of the ozone layer is destroyed if there had been no Montreal Protocol, if nothing had been done. Okay? Now what does that mean? That means huge impacts on crops. For somebody like me, I mentioned that if I go outside 15 minutes, I'll get a perceptible burn. In that world, it's 5 minutes, okay? So you go out and you walk for a quarter of a mile, you would get a perceptible sunburn. So this is an incredibly bad world. We don't want to live in that world. This is the one that we expect. Now, we can do, as I've already shown, we can do these projections of where ozone is going. Here we can see the observations. This shows a model projection. And now I put 2 model projections on here. The lower one is a world in which both ozone-depleting substances, it has a Montreal Protocol in it, they've been regulated, and so ozone is going up. But in one, greenhouse gases are regulated. In the other, greenhouse gases continue to go up, and in fact, ozone continues to go up. So the net impact of increasing greenhouse gases is that the ozone layer begin to pile up lots of ozone. So instead of a depleted ozone world, we're going to go to an ozone world where there's probably too much ozone. Now, what does that mean for the environment? I actually don't know. I don't think we know as scientists what's going to happen there. So let me say another word about what happened. This is, I love this picture. I owned a 1967 Ford Mustang Fastback. It was a hot car. I love this car. It had a CFC air conditioner in it. Okay? So I was using CFC 12 in that particular air conditioner. Here's a Tesla, a modern Tesla. It uses a replacement compound called an HFC, in fact, HFC 134A. In fact, in all your cars right now, you have that particular refrigerant in your car air conditioner. So this is the compound that replaced the CFCs. Now the beauty of this is a hydrogen, a fluorine, and a carbon. It doesn't have chlorine, so it doesn't destroy the ozone layer. The problem with HFCs, though, is their greenhouse gases. The particular HFC 134A is about, pound for pound, it's about 1,400 times more efficient at warming than CO2. So you could take 1 pound of this HFC 134A is equivalent to about 1,400 pounds of CO2. So the replacement compounds for the CFCs are greenhouse gases. And the question is, what are we going to actually do about these? Now this shows a particular HFC. This is HFC 23. You can see these are observations. They're increasing with time because we replaced the CFCs. There are many other HFCs. This is the one I talked about. It's in your car air conditioner, 134A. This 132 and 125, these are probably in your home air conditioning units. So all these HFCs are increasing with time, and these HFCs are all powerful greenhouse gases. So we solved the problem, that is the problem of ozone depletion. But in fact, those CFCs were also powerful greenhouse gases, but we replaced them with compounds that are also powerful greenhouse gases. So you could do a lot for climate if you figured out how to take these compounds and replace them with compounds that are both friendly to the ozone layer and friendly to climate. And in fact, there are technological solutions. So that goes back to the Montreal Protocol. The Montreal Protocol could, in fact, take action on these HFCs. We don't know that that's going to happen, but it might. So let me kind of summarize where we've been. So I told you a good story. We got rid of these CFCs. They're now regulated. They still exist in various places around the atmosphere, but they're slowly declining. That's a great story. In fact, the outcome of that would have been an environmental disaster if they'd kept growing. We used a lot of satellite information to take a look at the ozone problem. Most of the observations you've seen on this presentation have come from NASA satellites, including the Aura satellite that you can see here. Now, what does the future hold? Well, the future's in our own hands. We have two things you could regulate these compounds, and that may happen. But the one thing that we really need to do is we need to continue to look at the atmosphere, continue to make measurements of what's happening to our atmosphere. And that's where satellites like Aura and its follow-ons are crucial to knowing where we're going to be in the future. Thank you.
you.